If you are interested in the geology of Oregon and you want to find some on campus, the best place to look is in the Reed College Canyon. Oregon has fantastic geology, especially we have our painted hills out in eastern Oregon. We've got the Columbia River basalts. We've got all kinds of things that are exposed in the drier parts of Oregon, especially eastern Oregon. But here in western Oregon, especially in the Portland Basin that I'm going to be talking about today, and there's Reed College in the southeast portion. It's all covered with green stuff. It's all covered with grass and trees and houses and so forth. So we're lucky to have in the middle of campus sort of a trench that is dug right through that human and natural history. What a river does when it cuts down through the geology is it kind of cuts down through all the stories in that geology, and in the rocks and sand and so forth, it carries the stories along with it. And so having a stream or a river nearby is sort of like having an open air natural history museum. And the great thing about geology is you don't need fancy instrumentation to pick up a rock and wonder where it came from and how it was made and how it got there and how long it's been there. Sometimes you might want a small magnifying glass, but you don't even need that, nor do you need any special gear or, as I'm demonstrating here, a reckless disregard for any kind of fashion sense. You don't even need to really be a lover of the outdoors. A lot of work, interesting work now, is done on the computer or in the lab or even in our homes. So if we were to go down far enough and back enough in time, we'd get to a point where there was no land here whatsoever. It's just ocean and ocean crust and ichthyosaurs, plesiosaurs, and other small dying creatures. Everything that was happening in Pangaea at the time. That's the supercontinent where the dinosaurs were living and the angiosperms were developing and all that. And about 150 million years ago, the continent began to split right down the middle. And Asia and Africa went in one direction to the east, and the Americas went in the opposite direction to the west, leaving the Atlantic Ocean behind in their wake. And so that means that the North American continent for the past 150 million years has been pushing to the west. And what that means for us here in the Pacific Northwest is the story of subduction. And this is one of the fundamental narratives in geology since plate tectonics evolved from the 1960s on. The story here, the geophysics of this, I guess, is that ocean crust is heavier, moister, and more dense than continental crust. So when continental crust encounters ocean crust, despite the fact that continental crust might have mountains on it, it's lighter. It has more silica content and it's less dense. So as it pushes past, it overrides the ocean crust, and the ocean crust sinks down like a conveyor belt into the infernal depths of the Earth's mantle. This is really our fundamental understanding of the geology of the Pacific Northwest, and it shapes everything that we understand about the geology, the geography, and even the natural history of human history in the last 16,000 years or so. It is our master narrative. So quickly, a word about master narratives, because they can very quickly become cartoonish and sort of limiting of our imagination. It kind of blunts our appetite sometimes for more understanding more complexity. Moreover, for some people who identify with science as a force of discovery and exploration and liberation of thought, there are others who have a more skeptical view and feel that something more sinister is perhaps at work in the institutions of science, particularly the history to which geosciences in particular have contributed to the exploitation of the environment. Now, what I'm alluding to here comes out of conversations that have been had in the past few years addressing the problem of the lack of minoritized racial minorities in the geosciences. There are a number of efforts to address this. A lot of us participated in the Unlearning Racism in the Geosciences project last year with Dr. Vashon Wright. And there are other projects both on the level of diversity, equity, inclusion for both the professions and academics, and also grassroots efforts, community-based efforts to interject environmental justice issues into conversations about geoscience policy, environmental policy, and climate change. So I'll be returning to some of those projects for those of you who are interested in them. But we're not going to overturn the fundamental narrative here of subduction. We will find that it's weirder than it looks here in this cartoon. But the first consequence of having that conveyor belt is anything on that conveyor belt gets smashed up against the continent. So sand or silt or fish bones or tin cans or even islands that happen to be on that ocean floor will get pushed up eventually against the continent and smashed into or even sort of underneath the continent. So in this case, we believe that there was an island arc off the coast of Oregon that about 56 million years ago that was, an island arc. Think of something like Japan or Indonesia. So a set of islands, volcanic islands that here are named Silesia after the land that was taken from the Confederated Siletz tribe of Oregon, or the first land, the basement rock over which all the other rock is placed. It turns out that we think now almost all of the West Coast from Alaska all the way down to Mexico is composed of these successive accreted terrains that have been sort of rafted in up against the older continent, the North American craton, and smashed in and composed the land in California and Oregon and Alaska and Mexico, a virtual terrain wreck, if you will. Moreover, and this is really exciting and just has sort of emerged in the past 10 years, we now believe that Silesia was a hotspot and hotspot volcanism, and that links it to some other aspects of Oregon geology that I'll talk about later. So situating that little yellow Oregon Basin, that little yellow mark there in the northwest corner of Oregon, and I'm going to overlay a geologic map there. So what you're seeing in red is that ocean, is that island that smashed into us that we call Silesia. The red spots are places where it actually outcrops and you can find the basalts. The pink spots are places where we presume it to be, or we've discovered through drilling that it exists at a deeper depth. So overlaying it on the map there and kind of zooming into the Portland Basin, that would be our basement level. So if you went down deep enough underneath Reed College, you would get to those Silesia basalts. They don't outcrop anywhere on campus, but if you went a little farther south to Milwaukee, the Reed Canyon drains into the Johnson Creek, and Johnson Creek goes south to the Willamette, and that's a good place, a good spot where you can find these basalts just outcropping along the road on 17th there. And they're really old. They're, in some cases 50 to 40 million years old. Even though basalt is kind of a massive rock, it has cracks in it, and so water percolates through. And so it's very brittle. You can often kind of break it apart with your hands. And where the water has carried silica in along with it, it will precipitate the silica in any kind of crack or vug or bubble. And so you get these beautiful zeolite crystals that you can find, again, just by the side of the road and not with any special equipment, just breaking open the rocks and taking a look inside. Oh, this is, I should have mentioned that I'm communications director for the Geological Society of the Oregon Country. This is from one of our bike field trips, and we offer these field trips. We've been pulling over the car and stopping at outcrops for about 87 years, and I'll provide a link later if you're interested in coming on one of our field trips. So the ocean crust comes in at an angle to the North American continent, and it kind of torques the whole area. And what you're seeing, the big red arrow is the direction of the oceanic plate relative to the continent. The smaller arrows are GPS velocity vectors that indicate that the whole state of Oregon and also Washington has been rotating at the breathtaking rate of about 1 degree every million years. And this has the effect of kind of creating these pull apart basins, these rhombochasms where you get when you torque the land, it sort of opens up a basin. And that indeed is what the Portland Basin is. We've got two rivers running through it. We've got the Columbia and the Willamette running up into the Columbia. But this isn't a case where the rivers carved out the basin. It's instead the basin opened up starting about 50 million years ago, and the rivers have essentially been captured by the basin. You notice there that it's kind of rectangular in shape, and it's bounded by these northwest, east, southeast trending faults throughout, including the Portland Hills Fault. It's what we call in geology extensional topography. When you pull land apart, it kind of fractures. Parts of it slump down, parts of it relative to the slump down parts are forced up. This is the Basin Range terrain in Western United States, for example. So we get these Horst and Grabens, and Graben is from the German for grave, and I guess Horst is to raise up. In any event, if we look at the Portland Basin, now we're looking toward Reed College from the west toward Mount Hood. You see all these little lumps. And those are all the result of extensional topography. Those are all Horst, those are all chunks that have been lifted up. But fascinatingly, they're also surmounted by cinder cones. So somehow that extensional topography has provided the plumbing so that we can have all these little volcanoes, which we call boring volcanics because they're named after the town of Boring, Oregon. But they are really anything but, as you'll see. Now in the background, you've got Mount Hood. That's one of the Cascaden volcanoes, a different type of volcanism, a different mechanism that I'll be coming back to. So these boring volcanics, it's a phenomena. We've had about 60 or 70 of these volcanoes in the past several million years, and we're still in this period of volcanism. So we're one of the only cities that has a dormant volcano in our city limits. This is up from Mount Tabor, and you can see the layers of cinders that were extruded from the top of the volcano and then fell down along the sides and created that sort of the strata of cinders. We can expect, since we're still in this period of volcanism, that we'll have another cinder cone popping up here in the next, 15,000, 30,000 years. And it might look something like this if it came up in the metro area. But this isn't something that I really want you to worry about. We have plenty to worry about these days. Let's not worry about volcanoes, but I'll tell you a little later what we're actually worried about. So the next consequence of subduction, which is really one of the most important features of the story, is what happens when that oceanic crust gets forced down further and further into the mantle. Eventually, it starts to release the water that was in it. And that water rises as heat rises, as you can see in the diagram. And there's some geochemistry or geophysics that's happening there that causes the melting point of the rock above to decrease. So that rock melts and it rises as heat rises and eventually forms volcanoes. So the entire Cascade Range from Canada, Mount Baker, Mount Rainier outside of Seattle, Mount St. Helens famously, our Mount Hood here, Mount Three Sisters, Crater Lake is former Mount Mazama, and then down into California with Mount Shasta and Mount Lassen. All of those are part of this Cascaden system that, if you look from above, is basically the surface expression of where that slab has descended to the 60-mile point. And it's curved because that's the geometry of where when you take a plane and you insert it into a globe, it makes a curved shape. To give you a point of reference, that's where the Columbia is and where we are just a little bit south. Now, an interesting thing about when you see a river that crosses a mountain range like that in its entirety, what it tells us is that the river was there first and the mountain range came up afterwards. So the Columbia, or something like it, has been draining the Pacific Northwest for the past 50 million years. The Cascades in their current position have come up only in that position, only about a few million years in there. And that's critical because the Columbia has created a path through the Cascades, which is responsible for some of our most dramatic geological stories. This is the Columbia Gorge, through which 3 catastrophic floods have changed the course of Pacific Northwest and Portland Basin geological history and human history. One flood of basalt, the Columbia River basalt, 17 million years ago, a flood of molten lava that flowed from eastern Oregon and Washington through the Cascades all the way to the sea. One of rock and ice, the Missoula floods, that again flowed from the east through the Columbia Gorge, filling up the Willamette Valley and then out to the sea. And one of Euro-American settlers in the 1840s, 50s, and 60s, of which I am one of, essentially. I mean, I'm not that old, but in any event. Let's start with the Columbia River basalts. So this is a fantastic story. I mean, it's really wild that about 17 million years ago, these giant fissures opened up in Eastern Oregon and Washington, represented there by the white lines, and lava poured out. I mean, very much the same sort of runny lava that you would have seen in Hawaii back in 2018 in that eruption. And here it's represented in blue. You know, it's actually orange and black as it cools. So it filled up the whole Columbia Basin from that point on. And the only place it can get through is at that lowland where the Columbia cuts through the Cascades. And beyond that, it runs all the way to the ocean. And here you can see that Siletzia block is being labeled. So we have our first two layers. One is the Siletzia basalts, and then they get covered up 30 million years later by these Columbia basalts. This is from a recent field trip that we took out to Eastern Oregon. It's a drone flying over one of these dikes. The basalt dike is harder than the country rock. The country rock has eroded over the years. We're flying over something that's maybe, I don't know, 75 feet high and 30 feet across. I mean, this is the remnants of one of these giant fissures, these giant dikes that opened up and flooded. And you can see actually in the background, now that I'm looking more closely at this, you can see the layering of the basalts once they reach the surface, and then they just pool and fill the whole basin. Where they flood past us, and you can see a lot of these in the Columbia Gorge, you get these phenomenal Columbia basalt columns. And what's going on here is that as the basalt cools, it cracks perpendicular to the cooling surface. So here's a flood that was maybe 100 feet thick, more than 100 feet thick there. And as it cooled from the top, it cracked down, and you get these roughly hexagonal columns that, well, we have some very nice ones over by the Sports Center and some decorative artwork there. So they're often used, they're not very good building stone, but they're often used ornamentally, so you see them around. I think there's some in front of the library as well. The basalts run all the way out to the sea, and that, in fact, is what Haystack Rock is out at Cannon Beach. Now, here at Reed, Siletzia would be the lower base, the basement rock, and then on top of that, we'd have these Columbia basalts. If you're looking in the canyon, what you'd see is a little more nondescript. You'd see a gray rock. Break it open. Oh, but don't take it from the canyon. I have to say, since I took these photos a few years ago, there's now a sign that says, don't put your hands in the water. Don't take things out of so don't do that, but you can find it in other places. So we've broken open this basalt, and we see it's the little flecks of white are feldspar. Otherwise, it's mostly olivine and pyroxene. You don't need to know the mineral names, but that kind of gives you an idea of the story behind this gray rock, which you will see everywhere in pavement and in streams, and it's one of the most common rocks. It's not something that you see in other parts of the country to the extent that you do here, so we kind of take it for granted, but the humble basalt is a very important rock to us. So on top of that, we have the last flood story, or the next flood story, I should say, and that's the Missoula flood story. This takes us 3 orders of magnitude further in time. So now we're not talking about 14 million years ago. We're talking about 20,000, 12,000 years ago, during the last ice age, when giant continental ice sheets invaded the US from Canada, and then out there at Flathead, what's now Flathead Lake, it's in the Salish Confederated Salish and Kootenai tribes reservation up there. The drainages in that area got blocked by an ice dam, by the continental ice coming down. And occasionally that ice dam would fail. And as a consequence, the ice and rock and all the rocks that had been pushed into the lake would just flood out massively over a matter of hours and carve it out the channel scablands, went further down the Columbia Basin into the Wallula Gap, and then through the Columbia Gorge, then flooded the Portland Basin down into the Willamette Valley, sort of sloshed around in what we call temporary Lake Allison, and then eventually drained out entirely to the sea. In Portland, it inundated us here to a height of 400 feet. So it might have looked something like this. Had anyone been there? Had anyone been there? And here I'll defer to Dr. David Lewis at OSU, who's a member of the Confederated Tribes of Grand Ronde, and who's done work to show that there are Callipoolian accounts of people being inside the Willamette Valley and witnessing these massive floods. So there might have been someone up at the top of Mount Tabor. So as those floodwaters burst through the Columbia Gorge, the narrowness of the Columbia Gorge, 60 miles an hour, and flooded the Portland Basin, they slow down. And what you're seeing here is a geological map with lots of pretty colors that I'll explain in a moment. But as those floodwaters slow down, they drop the heaviest stuff. They drop boulders and gravels. And so what you get in east side Portland and Vancouver are these cross-bedded gravels. As the gravel gets pushed more and more, it creates these sort of diagonal beds that are really tough. And this is what the hill is as you go up the hill towards Chavez 39th. And the reason it's still there is because it's these cross-bedded gravels. When the water calmed and had days, weeks, or months to drain out, the finer sediments had a chance to settle. So here we get a different kind of deposit. We get something called a rhythmite, where you have a flood, and then as you see there, the gravel settle out first, and then over time, the sand and silt settles. Then maybe it's 50 years before another flood. Maybe it's a smaller flood, you get a little pulse of gravel, some sands and silts, then another flood. And this is how we know that there have been over 40 floods that made it to the Portland area and Willamette Valley. I'm going to show a quick video here of what that might have resulted in. Once again, you see that there's a lot more complexity than might be reflected in the geologic map, which shows us here at Reed College just in those fine-grained deposits. But the likelihood is that there's layering and erosion and a lot of stuff that's gone on. But that's what we would find if we were to dig down a few feet into the sediment and read. We'd find those rhythmites. A little to the east, the hill, are those coarse-grained deposits sloping down from Chavez. And to the west of us in the rhododendron gardens, it looks like there's some kind of channel. So those are channel deposits. And one theory is that that's where the Missoula floods drained out. Looking again at the canyon, we might pick up a humble quartzite here. Actually, not so humble. This quartzite is now famous. It's been in the Reed magazine. And it's a metamorphic rock, which tells us something right away, because this part of Oregon, Western Oregon, is too young for metamorphic rocks. This one, quartzite, is metamorphosed sandstone. So it had to be sand in the first place. It had to have once been granite that was eroded out of a mountain into a stream as a cobble, and then a boulder, and then a cobble, and then eventually sand down in a river, then covered up and became a sandstone, and under tectonic forces, metamorphosed under heat and pressure, and then uplifted and eroded out of a mountain again as a boulder, and then a cobble, and then this pebble. And we think that quartzites like this come from as far away as Idaho and Montana through the Snake, they're in yellow, or the Columbia, they're in purple watersheds. We think it comes from the Idaho fold belt, or the Montana fold belt. So this could be as much as 1 billion years old and traveled through countless civilizations to get here. Probably the last leg of the trip happened pretty quickly during the Missoula floods. So that probably happened over a matter of weeks to bring it here to the Reed Canyon. Even the sand has something to tell us. Normal sand looks kind of like this. It's a grainy photograph. It's rounded roughly. It's roughly rounded. That's a good way of describing it. The sand in the canyon looks like this. It's fractured. It's been through heck to get here. So that's a very interesting indicator of Missoula flood deposits, we think. Going back to the subduction picture, when the plate goes down, it gets stuck and periodically gets unstuck, and the result are catastrophic large magnitude earthquakes like the 2011 Japanese Tohoku earthquake. We used to think that there weren't earthquakes in the Pacific Northwest, although that was Western science that thought this. There are Native American accounts of thunderbird and whale that indicate that there was awareness of the dangers of earthquakes and the dangers of tsunamis going back millennia. One clue were these ghost forests at the Oregon coast. These appear at low tide in certain places, and they're tree stumps that if you look at the tree rings, if you do the dendrochronology and you count the tree rings, you find that they all died in the same year. They all died when the land dropped and there was a tsunami and the roots got covered up and the trees drown, and then they die in the next season. So that was a hint, but the final clue came from something called the Japanese orphan tsunami. Now, because of their tectonic situation, the Japanese keep very careful records of earthquakes and tsunamis. Usually, the tsunami comes about 15 minutes after the earthquake. But in 1700, there was a tsunami that had no earthquake associated with it. And so scientists have sort of run the clock backward and figured that if tsunami waves move about the speed of a jet airplane, about 500 miles an hour, that the last major Cascadian earthquake was here in January 26, 1700 at 9 p.m. Now, I kind of think that the 9 p.m. is scientists showing off, but in any event, looking at the record for the past 10,000 years, it looks like we've had a magnitude 8 or magnitude 9 earthquake about every 300 years. So the last one being 322 years ago, some geologists regard this as indicating that we're, as they say, 9.5 months pregnant for the next earthquake. Or another way of stating it statistically is that there's about a 30% chance of an earthquake in the next 50 years. A very important figure for all of the public policy that comes out of the question, well, how much do we need to be prepared for earthquake as opposed to, other disasters, climate changes and heat domes and things and wildfires and so forth. So it's a very real question for a lot of people. So going back to the geologic map, I'm going to overlay the geohazards map on top of it. There we go. And it's pretty much what it looks like, where red is bad and orange is a little less bad and yellow is much better if you are up there on the gravels. The worst place to be down by the river, where early in the 20th century, they piped fill out of the bottom of the river and they created more land by putting that fill in the marshlands. And that, unfortunately, is where 95% of the fossil fuels in Oregon pass through in what's called the critical energy infrastructure. So because it's on fill that's also very close to the river and very wet, that fill will liquefy. It's called liquefaction in an earthquake. It basically, the solid ground acts like a liquid. The tanks will fail, releasing toxic ammonia and fumes and chlorine. They will catch fire and then float down the river, causing environmental catastrophe for downstream communities. So this is what we worry about. And this is what some of us are engaged in at the moment in terms of trying to get some legislation passed in this short session that's coming up to give the state at least the power to regulate and require seismic mitigation plans for these tanks. Of course, this implicates a lot of questions about how much we want to be reinvesting in the fossil fuel infrastructure and how we're going to have any fossil fuels or energy available in the event of a disaster when transportation lines have been cut. A little bit better place to be is in those Missoula fine deposits that most of Reed College is in. So that's, if you're on campus now, you're sitting on fine deposits, you're probably okay if the water table is low below you, and I think it's about 40 feet below most of you who are on campus, but it's still a concern. The best place to be up the hill on those cross-bedded gravels anywhere in East County, even on those buttes like Mount Tabor and Mount Scott. Those are all much safer places to be. I mentioned that it's a magnitude 8 or 9 we're expecting at the coast. It won't be that here. It'll be more like a magnitude 6 or 7, but it will go on for something like 5 minutes. And so that's really the danger, is the length of the shaking and the structures that we're in. This is why you can't get into parts of the library right now, because the west wing of the library, built in the 1960s, was used unreinforced concrete, amazingly. And Reed is fortunate in having enough money to be able to do the seismic renovations. There are a lot of people for whom the renovations put retrofitting out of reach. And so this resulted in some pretty interesting politics a few years ago, when the city council passed an ordinance that required that all unreinforced masonry buildings have this placard on it, saying that this is an unreinforced masonry building, may be unsafe in the event of a major earthquake. Not good for your property values, and not clear what people should do when they read this. This was a particular problem for folks up in the Woodstock neighborhood, some of the small businesses up there, and particularly a problem for the historic Black churches in Portland. If you know your American history, you know that the Black church has been a cultural and political center of the Black community since Reconstruction or before. And so this hit particularly hard and drew the NAACP out in coalition with property owners and small businesses and music venues to oppose the ordinance. And actually, what brought me into working with NAACP on the environmental justice issues that are raised by these concerns. The ordinance was eventually pushed back, but the issue remains. We still have these unreinforced masonry buildings all around town that will result in loss of life. The issue we're pushing on now is the critical energy infrastructure, and trying to get concern for frontline communities, people who will have a harder time protecting themselves from environmental catastrophe. Let's go back to the hotspot for a moment. Hotspots do a funny thing when you've got a plate moving across them. They leave a trail of islands behind. That's what you've got out in Hawaii, is from east to west, successively older and older and older volcanoes, going back 50 million years all the way down the Emperor Seamount chain. The youngest being an underwater volcano, the Loihi, and the next youngest being the Kilauea volcano that we saw in action in 2018. So it's it's another one of these places where you see the geological story just looking at it, because as the plate moves over, the islands are older and older as you go. And that's what now we've discovered, that's another story, in addition to the subduction story, that links many of the geologic phenomena in the Pacific Northwest. So we started with Silesia, which I mentioned earlier was a hot spot. And then moving forward, it turns out that the hotspot's been responsible for some super caldera activities, that's responsible for some of the magnificent geology you see in Eastern Oregon. And then responsible also for those Columbia River basalts 17 million years later. And then we get a chain of volcanic calderas that move to the east, up the Snake River Canyon, 16 million years, 13 million years. As the North American plate is moving to the left of the screen, to the west, the hotspot stays in place and leaves a chain of super calderas behind, 10 million years, 6 million years, until we get to the Yellowstone hotspot. I remember hearing this from actually Professor Nick Zentner a few years ago. The hair on the back of my neck went up. It just was like it ties all of these mysteries together, maybe too patly. And this is where the science is right now, is kind of wondering to what extent subduction is responsible for much of this volcanism versus hotspot volcanism. It's very much at the forefront of the science right now. And it turns out this is a seismic tomography, where you create an image based on using earthquakes and putting the image together in supercomputers. And this is the work from Dr. Karen Sigloch, who's again at the vanguard of understanding some of this plate tectonics, these accreted terrain science. And it's just a lot weirder and more complex down there than initial cartoon that I showed you would indicate. It doesn't overturn our basic understanding of subduction, but just adds so much richness. And the combination of the subduction story and the hotspot story it's still blowing some of our minds. I mean, there's still a lot to be talking about. Nick Zentner is doing a wonderful job. He's a professor out at Ellensburg who has both a podcast, and he live streams his geology classes. You can also take a geology class from Professor Art Glassfeld, who's here in the room. I'm going to let him talk about that in a moment, but I want to show a couple things that we did, that Arthur and I did last year when we had to wear masks, and it was right after the ice storm. So But this is a little video that we did, a couple segments of video.
So these houses are now owned by Reed College here on 37th. They were constructed in about 1986. And that's about the time, according to the records that we've been able to see, that the wind dust point, the Native American projectile point, which is 8,000 to 10,000 years old, was found somewhere in this vicinity. Now, of course, that State Historical Preservation Office keeps a very tight lid on the location of those artifacts, and that's partially to protect the Native American heritage here. So we don't know exactly where, but we do know that it was found at a flaking site. That means that they were working the stone here. That's interesting for two reasons. One is, where were they doing it, and how much erosion has occurred since wherever they were exposed the flaking site. The other is, what was the material that they were working? There's not a lot, to my understanding, that's really good to make a projectile point in the Missoula flood sediments. There's basalts, there's quartzites, and I guess you could make an implement with a quartzite. But the better stuff comes from someplace like Mount Bachelor. It might have been traded at an obsidian or something. So, you know, that's the question, is what was it made of and kind of what was the site? Now, all of that is within really we're in what are called the ceded lands of the Grand Ronde tribe. And so it's really their concern. But I think it's important for Reed just to understand, as I did really for the first time, that these people were here. There are cobbles right at our feet. When you see cobbles in concrete like this, it's very likely that these came from a quarry in southeast Portland. And so even if you can't get down to the cobbles in the canyon, this is not a bad place to start to just look at the distribution. And heck, I guess one thing you could do is just count the number of apparent quartzites versus basalts and kind of come up with some sort of conclusion about the composition. So we're here at 28th Avenue, coming out of the canyon. And this is the place where the stream, having started up at the Ritmanis Pond and then coming westward, crosses 28th and at the Rhododendron Gardens and Golf Course makes a left turn. And then it heads south until it intersects the Johnson Creek, and then it heads further south down to the Willamette River. And if you look across, you can see there's a lake over there. So we have a second set of springs. The first set was at about 100 feet in elevation, back up at the headwaters where the water table meets the slope of the hill and comes out at 100 feet. The second set of springs is at around 60 feet, roughly, here in the Rhododendron Gardens. Another set of north-south running springs that flow into the Rhododendron Gardens golf course and then down through Westmoreland Park and eventually to Johnson Creek and eventually to the Willamette. Now, one of the things that's interesting about that ancestral channel is that it starts all the way up at about Division Street in the Willamette, and then it arcs past Reed College all the way down to Milwaukee, where it intersects the Willamette again, where Johnson Creek goes in. So one theory is that that's an ancestral backflow channel for the Missoula floods, and that when the floods came in, they ponded in temporary Lake Allison and then slowly drained out to the sea, carving features as they went and leaving this channel. Another theory is that this was an ancestral Willamette channel. It's about the right width and has about the right ratio of 1 to 11 curve to width. Don't quote me on that. But that this might have been a spot where people were fishing for salmon that was coming up the canyon here at a vista that would have looked out into the Willamette. Maybe 10,000 years ago. Of course, that's speculation.
If you're interested in these topics, join us at the Geology Talk meetup next Saturday. It's the fourth Saturday of every month at noon. You can get there through the meetup app, and we'll have a grad student, Andrew Dunning from Portland State Geology Department, will do the geology news, and then usually we have some special topic and sometimes show and tell. People just bring rocks. There's also another meetup at the Woodstock Wine and Deli once a month. That's, I think, the third Saturday of the month at 11:30. If you're interested in careers in geoscience or just the pathway from your chemistry degree or your environmental sciences degree or your English degree to a master's in geology at Portland State or other places and moving toward licensure, we're going to be doing another outreach event through the Oregon State Board of Geologic Examiners and having grad students talk about their experiences, both in grad school and toward moving toward the professions. There's fewer jobs. The jobs in the energy sector are on the decline. Jobs in environmental consulting are on the rise. Getting a good job that pays for your student loans is still a question in all of these professions, but we've seen a pretty good rebound in the geosciences after COVID or during and after COVID. If you're interested in community work, I would really encourage you to think about groups like NAACP has an environmental justice committee, and we have been focusing both on the unreinforced masonry issue that I mentioned before, but right now in this legislative session, we're focusing on getting some legislation passed that addresses the critical energy infrastructure and really getting some pieces of the legislation that address both environmental justice and climate change. So I will stop there.